Hello everyone. In this session, I will share with you a topic on signal recovery. To digitize an analog signal, first step is the sampling process. Now, how to obtain the analog signal from a sample signal. So this means how to recover the original signal from its sample. So for a sample sequence obtained from an analog signal XT, the important aspect is the recovery of the original signals from its samples. So this means it requires filling in the missing detail of the interpolating between the sample value. In signal recovery, only the ideal sampling will lead to a discrete signal Sn, in which the sample equals the strength of the impulse, the x NTS, multiplied with the delta t minus NTS at the sampling interns. There are four types of signal recovery. That is a Sinc interpolating function, step interpolation, linear interpolation, and rest cosine interpolating function. Now, let's talk about the ideal recovery and the Sinc interpolating function. The ideally sample signal, we call it XIT. Okay, I is referred to ideal. Is shown in the equation. Okay, ideal xt is the xt multiplied with the it, or xt multiplied with sum of the impulse strength. Okay, impulse is the impulse strength, or equal to summation of the x and ts. So this is the xt. If you want to change, this is the xt, right? Xt want to change the xn, so we multiply the x and ts. So this is from xt change to xn. So the xt change to x and ts. Okay, also multiply with the trend of impulse trend. Also equal to the xn. So x and ts equal to xn. So in this case, we can recover xt by passing the ideal sample signal through the ideal low-pass filter with a gain of Ts and a cutoff frequency of 0.5 S. This is the spectrum and its ideal low-pass, ideally sample signals. Okay, and then pass through a sinc function. Okay, pass through the xt pass through a sinc function. Then at the end, analog signal is recovered. So this is in time domain, whereas this is in frequency domain. So in time domain, the ideally sample signal pass through a sinc function, then you will obtain a xt. So this is we call as a recovered signal. So this is in time domain, and this is in frequency domain, whereas the bottom is the time domain. So the impulse response of the ideal low-pass filter is a sinc function. So given by sinc t over ts. This is as shown in here. So it's a sinc function here. So the recovered signal st can be described as the convolution. So xt is the ideal sample signal convoluted with the ht, or summation of the x and ts multiplied with the impulse strength convoluted with the ht, or this is already the discrete signal xn multiplied with the impulse response. So this describes the superpositions of shifted version of the ht weighted by the sample value xn. By substituting for ht, xt can be recovered exactly from the sample xn as a sum of the scale shifted version of the sinc function. So xt can be recovered from the sample of xn and the sum of the shifted version of the sinc function here. So this is the formula for Sinc interpolating function method. From this graph, we say that there are four Sinc interpolating functions. The first one is the green color, okay? The green color. the green color sinc function has a peak of 1 at n equal to 0. And the blue color, this is the blue color has a peak of 2 at n equal to 1. Whereas the purple color has a peak of 3 at n equal to 2. And lastly, the orange color has a peak of 4 at n equal to 3. Therefore, we can say that at each sampling instant, the sample value xn, okay, the sample value xn is replaced by a sinc function. Okay, all this is a sinc function in which the peak value equals Sn and the zero crossing occurs at all other sampling instants. So if we simply redraw all the peak value, so just now we have all the peak value, right? So we simply redraw all the peak value. This is how the graph looks like. So this is a peak. So this is the graph looks like if we simply redraw or pick the maximum value. So the recovered signal is the sum of the sinc function centered at the sampling instant, okay, at 0, 1, 2, 3. Okay, so the 0 of this sinc function occurs at the multiple of the sampling interval. So if low-pass filter is used and the impulse response is the HFT is equal to 2TSB sinc to BT, so the recovered signal XC can be described by the convolution. Okay, so XC equal to ideal sample signal convolute with the HF or equal to this one. Okay, so this is valid only for overall sample signal with TS less than 0.5 divided by B per B. However, we say that the sinc interpolation is unrealistic from the practical viewpoint. Do you know why? This is because the infinite extent of the sinc means that it cannot be implemented online, and perfectly reconstruction require all the past and future values. So since the sinc function varies smoothly, it cannot properly reconstruct a discontinuous signal at the discontinuity, even with a large number of values. That's why it's unrealistic. So the sinc interpolation is also referred to as a band-limited interpolation, by which all other schemes are measured in their ability to reconstruct band-limited signal. So for the interpolating function, in order to obtain a good approximation, the interpolate approximation axis should match at the sampling instant NTS. So the suggested HIT should be equal to 0 at all sampling instants except at the origin. The interpolate signal, okay, or in the short form is X bar T, is the convolution of the HIT with the ideally sample signal. So it's a HI convolute with the ideally sample signal, or equal to a summation of the XN and with the trend of the impulse response. So at the sampling instant T equal to KTS, the interpolating function equal to 0 unless n equal to k when it is equal to unity. So as a result, the interpolate signal exactly equal xt at each sampling instant. This is maybe hard to understand, but later I will give you an example. Therefore, for the interpolation in practice, there is no best interpolating signal. Some are better in terms of their accuracy, cost, effectiveness, or numerical implementation. The second step, or the second method, is the step interpolation. Okay, step interpolation use a rectangular interpolating function. Okay, so equal to rectangular t minus 0.5 ts over ts to produce a staircase approximation of xt. So at any time between two sampling instants, the reconstruct signal equals the previously sampled value and does not depend on any future values. So this is used for real-time processing, where the output is produced at the same rate as the incoming data. A system that performs step interpolation is just a zero-order Hall system because it's a staircase approximation. So a practical digital to analog converter or DAC is for sample signal use a zero-order Hall for a staircase approximation, followed by a low-pass filter for smoothing the step. The third method is the linear interpolation. Linear interpolation uses the interpolating function ht equal to 3 t over ts to produce a linear approximation to xt between the sample values. Okay, so we have a linear approximation between the sample and the value. So for linear interpolation, the reconstruct signal is equal to the xn plus with the increment. This is the increment that depends on the slope of the line joining the Sn and Sn plus 1. So the t is in between nts and n plus 1 ts. So for this operation, it requires one future value of the input and cannot actually be implemented in real time also. So this system performing linear interpolation are also called first order Hall system. The fourth method is called rest cosine interpolating function. Rest cosine usually used for pulse shaping in digital modulation as it able to minimize inter-symbol interference or called ISI. So this Sinc interpolation function forms the basis for several others described by the relation of the ht equal to gt Sinc t over ts. Okay, where g0 is equal to 1. And this is the common formula or function for this rest cosine interpolating function. So HRC equal to the cos divided by 1 minus 2RT divided by TS. And multiply with the Sinc T over TS, where the R is from 0 to 1. R is so-called the roll-off factor, and HRC equal to 1 at t equals 0 and 0 at other sampling instant. So this rest cosine interpolating function allowed the fewer past and future value to be used in the reconstruction. And the terminology of the rest cosine is actually based on the shape of its spectrum. For R equal to 0, the rest cosine interpolating function reduces to Sinc interpolating function. So I have explained the 4 types of signal recovery, 4 methods. So the first one is a Sinc interpolating function, second step, third is a linear, and the fourth is a rest cosine interpolating function. So here, for the Sinc interpolating function, we recover the xt by passing the ideally sample signal through an ideal low-pass filter with a gain of Ts and a cutoff frequency of 0.5. And this is the formula that you will use to find using the Sinc interpolating function. Next is the step interpolation. So step interpolation uses the rectangular interpolating function to produce the staircase approximation. So this is the ht for you to find the step interpolation. So the reconstruct signal equals the previously sampled value and does not depend on any future value. Whereas the third method is the linear interpolation. So this method depends on slope of the line joining Sn and Xn plus 1. Okay, so this is the formula, and t is in between nts and n+1 ts. The last one is the rest cosine interpolating function, and this is the formula to find the rest cosine. So the calculation for the rest cosine would be a bit lengthy. Now let's look at the example. Given the xn equal to -1, 2, 3, 2, and ts equal to 1, what is the value of the reconstruct signal xt at 2.5 seconds that result from the four type of the signal recovery method? Okay, we will look at it one by one. The first question is to use the step interpolation to find the reconstruct signal xt at 2.5 seconds. So your xn in the question is -1, 2, 3, and 2. Okay, this is your xn. So the t, so -1 is at t equal to 0. So this is the signal. This is t equal to 1, t equal to 2, and t equal to 3. So for the step interpolation, we will use this formula, the ht equal to the rectangular t minus 0.5 ts over ts. So ht equal to rectangular t minus 0.5 ts over ts. Okay. So t is referred to the question, that is 2.5 seconds. Okay. T is 2.5 minus 0.5 ts. Ts given in the question is 1. So you just substitute value is 1. Okay, so this is equal to rectangular 2. So rectangular 2 means that you will follow the ht will follow the value at rectangular 2, at the value of 2. So this means if we draw the signal of xn, you will have the -1, you will have -1, and then this is a 1, 2, 3. Okay, and then -1, you have the value of 2, and then you have the value of 3, then you have the value of 2. So for the step interpolation, you will follow this line. So this is your signal. So for rectangular 2, so you will follow this value, rectangular 2. So rectangular 2 is, what's the value? The value is at 3, because now you want to find for the value at t equal to 2.5. So this is second. At t equal to 2.5, the value will be follow the value of 2. So the value is 2. T equal to 2 for the xn. So the reconstruct signal is at 2.5. This means you get the value of 3. Okay, the value of 3. This means the signal value at t equal to 2.5 seconds is simply the value at t equal to 2. Okay, next we use a linear interpolation. For a linear interpolation, we follow this way, this formula. Okay, xn plus t minus this one, we follow this value. Okay, so the formula must satisfy the equation like this because it's a linear, right? So t in your question is 2.5. So n ts, so n ts is 1, then n plus 1, ts is also 1. So this is n, and this is n plus 3, n plus 1. So this is from 2 to 3. 2 plus n plus 1 is 3. Okay, so it's from 2 to 3. The value you follow is from 2 to 3. So the signal value at t equal to 2.5 is just simply the average of the value from 2 to 3. So it's the average of the value at t equal to 2 and t equal to 3. So the reconstruct signal at 2.5 is average of the value at 2 and the value at 3. The value at 2 is 3 and the value at 3 is 2. So the value at 2 is 3 and the value at 3 is 2. So 3 plus 2. So this is the when t equal to 2 and this is the value for t equal to 3. So 2.5, so it's equal to 2.5. Just now I show you the formula. We didn't use it because this is quite simple, because it's 3 plus 2 divided by 2, so it's get 2.5. You don't need to get that complex formula unless you have a very difficult numbers difficult to get the linear value, so you can use that formula. Okay, then the third method is the Sinc interpolation. So the formula for the Sinc interpolation is the summation from minus infinity to infinity xn Sinc t minus n ts divided by ts. Since the xn, your xn is -1, 2, 3, and 2. So -1 is from 0 to 3. So your k value is from 0 to 3. Xn Sinc t minus n ts. So ts is 1, so it's t minus n only over 1. Okay, so I would say you just t minus n will be enough. Okay, now you start xn from k equal to 0, that is -1. So the first value, -1. Sinc, so this is so start with k equal to 0. So x0 is -1. Sinc t minus 0, so it's t. Plus with when k equal to 1, so x1 is the value is 2. 2 Sinc, so t minus 1. Okay, and then plus with when k equal to 2, so you have x2 value is 3. So 3 Sinc t minus 2 plus with when k equal to when n equal to 3. Sorry, this one is not k, this one is n. When n equal to 3, you have the value of 2. So it's 2 sin t minus 3. Okay? So I simplify it. So the t in the question is 2.5. So you get 1.5 here plus 3 sin 2.5 minus 2, you get 0.5 plus 2 sin 2.5 minus 3, you get negative 0.5. Okay, then you need to solve each sinc function, okay, separately or one by one. So I have the formula sin A equal to sine pi A over pi A. So this one must do it in radian. Okay, must do it in radian. All right. So for the first one, we just substitute sin equal to sine pi A. So sine pi A. A is referred to 2.5. So 2.5 pi over 2.5 pi. Okay, plus with the second one, 2 sin. So 2 sine 1.5 pi over 1.5 pi. Plus the third one is 3 sine 0.5 pi over 0.5 pi. And then plus with 2, the last one is a 2 sine negative 0.5 pi over negative 0.5 pi. So this will equivalent, okay, when you press the calculator, you will get this value. So the answer is 2.6315. It's more or less near to 2.5. Even though not exact, you get the same as 2.5. Alright, so the last method is use the res cosine interpolation. And then with the r equal to 0.5. So the reconstruct signal. So this is the formula for the res cosine interpolation function. So we will use this equation. So similarly, the n is from 0 to 3, xn sin t minus nts divided by ts, and then multiply with a cos pi r t minus nts divided by ts over 1 minus 2r t minus nts divided by ts square. So this will equivalent to sin t minus n cos 0.5 pi t minus n 1 minus 2 0.5 t minus n square. So the r is, you substitute is 0.5. So now when n equals 0, x0, you get negative 1 sin t, when n equals to 0, so it's just t only. So cos 0.5 pi t divided by 1 minus t squared. Okay, plus with when n equal to 1 is 2, you get 2 sin t minus 1. Then multiply with the cos 0.5 pi t minus 1 divide by 1 minus t minus 1 square. And then plus with 3 sin t minus 2 cos 0.5 pi t minus 2. Then divide by 1 minus t minus 2 square. Then plus with 2 sin t minus 3 cos 0.5 pi t minus 3. So this is 1 minus 3 minus 3 square. Again, we simplify. You substitute the value. Substitute the value of t equal to 2.5 cos 0.5 pi 2.5. If you want to directly substitute also can, just that I want to show you step by step so that you can follow. So this is 2 sin 1.5. Okay, 2 sin 2.5 minus 1, 1.5, then cos 0.5 pi 1.5. This one is divided by 1 minus 1.5 squared. And then plus with 3 sin 0.5 multiply with cos 0.5 pi multiply with 0.5 divide by 1 minus 0.5 square. And then lastly, we have a 2 sin negative 0.5 cos 0.5 pi minus 0.5. So 1 minus 0.5. Okay, so the first one, if you solve this one, you will get negative 0.0171. And then you solve the second one, you will get minus 0.2401. And then you solve the third one, you will get 1.8006. And then lastly, this one will give you the answer of 1.2004. So when you total out, you will get 2.7438. So this is the reconstruct signal at t equal to 2.5. You will get 2.7437. So this value is even bigger than the previous one. So rest cosine is the biggest number compared to the Sinc interpolation. So only the step interpolation or the linear interpolation you will get the same value. Okay, so that's all for the signal recovery. You have 4 types of the signal recovery. Okay, hope you can understand each of them, and thank you for watching. Hope you can enjoy, and if you like my video, please remember to like my YouTube video. Okay, thank you class.